Okay, so let's look at a different problem now. The previous problem was about the charged object in a uniform electric field, uniform magnetic field. Now let's add a magnetic field. Let's add an electric field to our system. So let's just assume we have magnetic field in this direction. Let's choose our coordinate axis to be x, y, and z. And there is also a uniform electric field, or let's say the magnetic field is in the x direction. In the z direction, there is an electric field. So what will be the motion of this particle, given some initial velocity v0? Let's see, what do you expect? Let's assume that we have this particle initially at rest. So it is at rest. So there is an electric field in the z direction. There is a magnetic field in your direction. So what will be the motion of this particle? So which direction do you expect the particle to move on the average? It will be doing some complicated motion. But will it be, let's say, the electric field is in the z direction, it can just move in the z axis with a complicated motion. That is one possibility. Or it can move in some other direction with a complicated motion. What is your expectation?
Straight line.
On the y-axis, straight line on the y-axis. Okay, that's a guess. Semi said that it will be moving in the y direction with some complicated motion. Some ellipse along the, some helizon along the z-axis. Let's see. Let's try to solve it. Well, first of all, let's see. The force due to the electric field will be in the z direction, right? The force due to the magnetic field will be perpendicular to the x-axis all the time. So it will have a y component and a z component. So the net force in the x direction will always be 0. There can never be a force in the x direction in the system. So whatever the initial x velocity is, it will just do some motion with constant velocity in the x direction. So that's not that interesting. So we will be assuming that Vx is, to start with, it is 0. So the force, the magnetic force, or let's write the total force, QE plus V cross P. This is the total force acting on my object. E is its component in the z-axis along the z direction. V is, let's just ignore the x component, it will not contribute to the force anyway. Vy in the y hat plus Vz in the z hat cross B in the x hat. Let's take these cross products. So it's Q times Ez hat plus, okay, Vy times B. What is y hat cross x hat? Minus z hat. Plus Vz times B. What is z hat cross x hat? No, that's y hat. So this is the total force acting on my object. So force will have a y component, which will be equal to Q times Vz times B. And it will also have a z component, which is Q times E minus Vy times B. And this should be, the y component of the force should be equal to m times the acceleration in the y-axis, and the z component of the force should be mass times the acceleration in the z-axis. Now, if we denote the position r as x in the x hat plus y in the y hat plus z in the z hat, Then x double dot is 0 because there is no force in the x direction. Y double dot, m times y double dot, this is mass times ay. This is equal to q times z dot b. This dot notation, by the way, is just the time derivative. Whenever you see a dot, it is just time derivative. 2 dots, second time derivative. And mz double dot is equal to q times e minus y dot b. And now we have to solve this equation.
Should that be Q downwards here?
Yes, qy dot b. Well, the easiest would be just take the time derivative of any one of them. Let's say we can take the time derivative of this one. Then it will be z triple dot, the third time derivative of z, will be equal to the time derivative of this one is 0 minus q times y double dot. Well, we already know what y double dot is. Just put y instead of y double dot, use this expression. So m times the third time derivative of z is equal to minus q, the second time derivative of y. Well, the second time derivative of y is nothing but q times q over m. This is equal to minus q times b. The second time derivative is q over qb over m times dz by dt. Or the second time derivative of dz by dt, this should be equal to minus q squared qb over m, all of this squared dz by dt. So this basically tells me that the time derivative of z is such a function that its second time derivative is equal to itself with a negative constant. Well, that we already know from harmonic oscillator. You should already remember this. So dz by dt should be equal to, let's say, some coefficient. Let me call it small a. Or let me call it small a over m, a over omega, cosine omega t, plus small b over omega, or let me choose this plus this one, minus sine omega t. No, sorry. Let me change my definitions of constants, where I define omega to be qb over m. Well, this basically tells me that z as a function of time t is equal to a times sine omega t plus b times cosine omega t plus c. This is the z motion. Well, this is why instead of calling a times omega a constant, another constant, I just define a such that there's an explicit omega over here so that it doesn't appear over here. I could have, if you wish, just call this a omega a new kind of constant. These constants a and b are determined by your initial conditions. Now we still need to find y. Let's look at this one, this equation. Well, this tells me that y dot is equal to q times e minus m times z double dot divided by Q, B. So y dot is, or dy by dt is equal to E over B minus M over QB. Well, Z double dot. Z is this one over there. So Z double dot is just, well, if it was just the A's, and let me just write it explicitly, that is omega squared minus QB over M times A sine omega t plus B cosine omega t plus C. No, there's no C. So these cancel. Dy by dt is equal to E over B. Sorry, omega is not square root of this. Omega is QB over M. So here I have another QB over M. Minus omega A sine omega t plus B cosine omega t. I can integrate this. Y of t is equal to E over B times t plus A cosine omega t minus B times sine omega t plus some constant d. This is Ry. And this is our Z. Now let's see what this tells us. If you look at the Z expression, Z of t, let's look at Z of t minus C, at C is that constant over here. I have the sines and cosines. The maximum value of A sine omega t plus B cosine omega t would be A squared plus B squared under the square root. That is the maximum possible value. So the Z coordinate oscillates around this value C with an amplitude given by this number over here, Z. If you just look at the Z coordinate of the particle, it just goes up and down. Now let's look at the Z axis. Z is the direction of the electric field. We have the electric field in that direction. So as the particle moves, the Z component just goes up and down. Now, on the other hand, let's look at the Y component. So Y of t minus E over B times t plus d. Again, let's look at this absolute value. Again, I have this A and B's. Again, this will have the amplitude A squared plus B squared. So again, this Y coordinate oscillates, but this time it oscillates around this value. Well, this is some motion with constant velocity. So you have this center, kind of, that is moving with constant velocity, and the Y coordinate is just going up and just slightly deviating from this central value. Now the motion, if you just plot it, given some, let's give it some numbers. Let's just assume that at t equal to 0, you see we have these four unknown constants. We don't know A, we don't know B, we don't know C, we don't know D. Basically, that is because, you see, we have two equations. Here we have two second-order equations. The solution of a second-order equation involves two unknowns. We have two of them, so we should have four unknowns to be fixed by the initial conditions. So we should specify the initial conditions to determine what these A, B, C, and D are. Y at 0 is equal to Z at 0. This is equal to 0. I'm just setting my origin to be the initial position of my object, and I'm just releasing it from rest. What should be the boundary conditions? Well, let's see. At t equal to 0, 0 is equal to a plus d. 0 is equal to, this is y of 0. Z of 0, this is b plus c. Okay, these are the two conditions we have. Well, if you take the derivatives, z dot at 0, which we are given to be 0. If you look at our expression for z, take its time derivative, z dot will be just a omega. So already we know that a is equal to 0, but so is d from this equation. So we already determined two of them. Let's look at y dot 0. This is e over b minus b omega. D is already 0. This should be equal to 0. Or small b should be equal to e over b times omega. This is equal to minus c. So y of t, this is equal to e over the magnetic induction times t. A is 0. B, we said that it is e over small b. Well, omega q b over m. Sine omega t. D was 0, and z of t is equal to b, which is e over b qb over m cosine omega t minus 1. So basically it makes a circle around this point, which moves with linear velocity. So the motion will look something like this. This y, z, this is y, this is z. This will be the motion. And remember, this is the direction of the electric field. And this is the direction of the magnetic field. So the magnetic field is increasing its velocity. It is giving it a velocity. No, the electric field. The magnetic field rotates the velocity up to this point. Now, when it reaches this point, it has a high velocity, but it's moving in this direction. Now, it has a velocity in that direction, so it keeps moving in the same direction. But if it's moving backwards now because magnetic field has rotated it. But that means the electric field is slowing it down. It will slow it down, and eventually come to a stop in the vertical direction. But then the electric will push it in the upward direction, so it will just repeat itself. It will come to a stop and then repeat itself. This is called the cycloid. Well, this is basically what's going on also in the wire. The charge is trying to go on a cycloid in a magnetic field. But for example, if you put some If the surface of the conductor is somewhere over here, or let's say the electric field is along the conductor, so if the surface of the conductor is over here, it will just collide with it and bounce back, exerting a force on the wire. This is another example where you say this object is gaining velocity. No, not really. It started with 0 velocity, but you see the y component on the average has a velocity as a constant velocity in the y direction, not in the direction of the electric field, in a perpendicular direction to the electric field. So that's what the magnetic field rotates the work done. Although the work done by the electric field is pushing the charge in this direction, the kinetic energy that this charged object gains forces it to move in the y direction, in the perpendicular direction. Well, you see, this is what we found. If you just take the time derivative, you get a constant time derivative from this one, and then you get a cosine from this one. The cosine oscillates, so if you take the average velocity in the y direction is just this constant. This is just 0. It averages to 0. The y of t. Well, you see what I did. Let's go back. So let us just review from this step. First, we identified the force. Well, the force is mass times the acceleration, or mass times the second derivative. So I just wrote the x, y, and z component of force is equal to mass times acceleration. So on the left-hand side, I have the mass times acceleration. On the right-hand side, I have the forces. This is the x component of the force. There is no x component of the force. It is 0. The y component of the force is proportional to the velocity in the z direction, which is z dot, the time derivative of the z component. And in the z direction, the force is, there is a constant due to the electric field plus another force due to the y component of the velocity, which is y dot. So this is what's called a second-order coupled system of differential equations. We have two of them. So the y equation depends on z, z equation depends on y. To uncouple them, what we do is we just take the time derivative of the second equation. That gives me an equation for the third derivative of z. But the third derivative of z is this is a constant. It's proportional to the second derivative of y, but the second derivative of z is proportional to the first derivative of z. So we have an equation that relates the third derivative of z to the first derivative of z. Or if you think in terms of the first derivative of z, this is our function. So it is a function that relates the second derivative of this derivative to itself. And the solution is just this oscillatory solutions with that angular frequency, omega is qb over m. Now, dz over dt should be just some linear combination of cosine omega t and sine omega t with arbitrary coefficients that should be fixed by initial conditions. And I just denoted those arbitrary coefficients by a omega and minus b omega. So then I have this is my z. The derivative of z should be equal to this one. Just integrate both sides. You get the z at the time t is equal to this a sine omega t plus b cosine omega t plus c, which is some arbitrary constant. Yes? This equation. The second derivative of some function is equal to the function itself with a negative coefficient. This tells me that it's an oscillating function. It's the harmonic oscillator equation. And so we know that in terms of these unknown coefficients that needs to be determined by the initial conditions. Now, what else do I know? This was my equation along the z direction. The second derivative of z should be proportional to this number. The mass times the second derivative is this constant minus q times the first derivative of y. So I can solve for the first derivative of y. And I obtain that the first derivative of y is q times e minus mass times the second derivative of z divided by this number. So I did some cancellations. And well, the projector also canceled our lecture. Okay, I have this constant E over B. And then I had this y dot is equal to E over B minus Z double dot divided by QB times minus M. So this is what I obtained for the y dot.
Hocam nereden karar verdik Z'nin ve Y'nin first derivatiflerini sıfır olduğunu?
Let me come to that later on. I don't know yet. I mean, I don't know whether the first derivative or the y is 0 at t equal to 0. I don't know that one yet. So I don't know these a, b, and c coefficients yet. Now I solve for y dot, and y dot is equal to this one. Just separate them. I have minus e over b minus m over qb times z double dot. Well, z double dot you already have the expression for z. Well, z double dot is nothing but minus omega squared times a sine omega t plus b cosine omega t. So this I just put it back. Now remember, omega squared is q squared b squared over m squared. So y dot just turned out to be e over b minus m over qb. Well, there is a minus sign over here, another minus sign over here. So that makes a plus. And omega squared is q squared b squared over m squared. A sine omega t plus b cosine omega t. This is my y dot. Let me just make some simplifications. qb over m, they cancel one of them. Now we need to integrate this. This is the derivative, time derivative. So if you just integrate it, y as a function of time should be e over b times t, and a plus minus a cosine omega t over omega plus b sine omega t over omega, and all of these are multiplied by qb over m. Well, qb over m is omega. Okay, now I have made a mistake in the calculation. So omegas, they will cancel, plus some other constant d. Now I have y of t. E over b times t minus a cosine omega t plus b sine omega t plus d. No, I didn't make any mistakes. So this is minus a cosine omega t plus b sine omega t. I think this, well, just check the signs. I think this one is correct. So we know y of t, we know z of t is a function of time. Well, there are certain general things we can say about this motion without really knowing what the initial conditions are. And those are these conditions. You see, if you have this function, if you have a cosine omega t plus b sine omega t, this function is always between minus square root of a squared plus b squared and plus square root of a squared plus b squared. Always. So that basically tells me that whatever these coefficients a, b, c, and d are, zt, the z component, is always around c. It oscillates around c. And the y component always oscillates about this number. So this point basically moves with constant velocity. So I have kind of, there is this motion, this component which is moving with constant velocity, and the z and the y components, they are just oscillating around that. If you look at the problem more carefully, the trajectory is basically take a wheel, fix a point on the wheel, and roll the wheel. So at this point, the trajectory of this point on the wheel as the wheel is rolling and moving is given by this expression over here, by these expressions. This is the general solution. Now then, we didn't specify any initial conditions up to this point. We can just pick any initial condition you like. And where do you put your charged object? You can put it on the origin, put it at some other point. It's up to you. You can give it some initial velocity, whichever velocity you like, it's also up to you. Now in these initial conditions, what I said is just to keep things simple, let's assume that I choose my origin as the position of my charged object at the initial point, at t equal to 0, so that I know that the y and the z coordinate at t equal to 0, they are both 0. And let us assume that at t equal to 0, I just release it from rest. If this is the case, then I can determine these coefficients a, b, c, and d. And they turn out to have these values written over here. And these are my y and the z solutions. The coordinates of my function is the coordinates of the position of my charged object as a function of time. Now, if you look at these solutions, what do they satisfy? Y of t minus e over b times t squared. You see, what I did is I just isolated this sine term. I isolated this sine term, and y of t minus e over b of t just gives me, t squared gives me this coefficient squared times sine squared. I will isolate the cosine term over here. But sine squared plus cosine squared will just give me 1. Plus z plus e over b omega squared. This is equal to e over b omega squared. Well, this coefficient over here is nothing but e over b omega. But this is nothing but the equation of a circle with its center moving in time. So this coordinate E over bt and minus E over b omega is the center of, I mean, we had this wheel example. These are the coordinates of the center of my wheel. And this coordinate is always at the same distance from the center of my wheel.
O zaman bu aslında dairesel hareket yaparak.
It is doing a circular motion, but the center is being translated. So, I mean, if the electric field was 0, I mean, you can just set E equal to 0. If you set E equal to 0, it's just circular motion. That's our previous example. That's E equal to 0. If you create an E in this direction, well, of course, there is a problem that initially it is 0 if E is 0, so V always stays to be 0. But let's say you give it some initial velocity, and then it will just do this circle. If you turn on the electric field in this direction, so this will be its trajectory. It's always still doing this circular motion, but relative to a point that is moving with constant velocity.
Nasıl hocam? Relatif point. Relatif point bir şey değil mi?
You will move with me. So now I'm making a circular motion. We will move together. Do you see a circular motion? Now sit down. I'm doing the same motion. Do you see a circular motion? No. It is making this weird motion. It is doing a circular motion relative to a point that is moving with constant velocity. If you go to that reference frame, which moves with exactly the same velocity as the center, you will see a circular motion. But that is in a different reference frame. In the original reference frame, you will see this weird motion. Okay, let me close today's lecture by a question for you. So this is the force acting on a charged object in an electric and magnetic field. Now, do you remember Galilean relativity? So it basically says that the velocity depends on your reference frame. So if you choose a different reference frame which is moving with velocity relative to the initial one, the velocity will be different. But as long as you are in an inertial reference frame, the acceleration will always be the same. You go to a different reference frame which is moving at a constant velocity relative to your initial reference frame. Both of the reference frames will be inertial reference frames. They will both measure different velocities, but they will measure the same acceleration. You agree? Remember? But same acceleration just basically means that they will be exerting the same force in every inertial reference frame. An object should feel exactly the same acceleration in every reference frame. Now let's look at this expression. If I go to a different reference frame, V will be different, but the force should be the same. Both the electric field and the magnetic fields should change, but we are not referring to anything that would cause a change. You see, the force should be the same in every inertial reference frame. Let's see, it has this force in one reference frame. Now I change to a different reference frame. Let's say I go to a reference frame which is moving with this velocity v. Then in that new reference frame, my charged object doesn't feel any magnetic force. This is 0, v is 0. So how come? As your friends stated, the force should stay the same. That basically means that the electric field and the magnetic field, they should look different in a different reference frame. We are not, in our, at least treatments up to this point, we never refer to our reference frame though. Well, in fact, we did refer to our reference frame. We are choosing a particular reference frame by stating that we are looking at statics. Being static is a frame-dependent quantity. So if you have a point charge over here at rest, it will be at rest in one reference frame. In that reference frame, I can treat this problem as electrostatics. But if I start moving in that new reference frame, my charge density at every point, my charge density will be changing in time. So that's no longer an electrostatic problem. So this is kind of an indication that we are still missing the dynamics. The dynamics will have important modifications in our formalism. Otherwise, we have to give up Galilean relativity, which we wouldn't like to do. Okay, that is that we will study when we start dynamics. Okay, see you on Monday.